All right, let's talk about TensorFlow. If you're anywhere near the world of AI and machine learning, you have absolutely heard this name. It's this powerhouse that came out of Google, and it feels like it's just everywhere. But what is it actually doing under the hood? Well, today, we're going to pull back the curtain and demystify it. And you'll see why it's not just another library, it's a whole new way of thinking about computation.
So let's just get right to it. The million-dollar question. What is TensorFlow really? I know it can feel super intimidating and complex, but as we're about to find out, the whole thing is actually built on one single, really elegant idea.
And here's our game plan for today. We're going to start with the basics, then we'll compare it to something you might already be familiar with. From there, we'll uncover its core two-step process, and this is the real key. We'll look at the building blocks, see how they snap together to build a model, and wrap it all up with the one big idea you need to remember. Sound good? Let's dive in.
Okay, so first things first. Before we get into the nitty-gritty, where does TensorFlow even sit in this huge, sprawling world of AI tools?
It's really important to know that TensorFlow is not an island. It lives in this super busy, vibrant ecosystem of deep learning tools, what a lot of people call the package zoo. You've got Torch, Caffe, Theano, the list goes on. But TensorFlow, because it has the full weight of Google behind it, has become this absolute giant in the field, especially when you're talking about massive industrial-scale projects.
So here's the formal textbook definition. Let's just break this down. First off, a tensor, that's just a fancy word for an array of numbers. Could be a simple list, could be a grid, or a cube of numbers. You get it. So it's for doing math. But the real magic, the secret sauce, is in that last part, automatically computing their derivatives. This means it handles all the ridiculously complex calculus that makes machine learning work for you. You don't have to do it. That's a huge game changer.
You know, to really wrap your head around TensorFlow, it helps a ton to compare it to a library that a lot of data folks already know and love, NumPy. Because this comparison is what reveals the huge conceptual leap you have to make to really understand TensorFlow.
So you look at the code side by side, and it looks almost the same, right? You're making an array of zeros, you're summing things up, checking the shape. Yeah, the syntax is a little different here and there, but the intent feels identical. You might think, oh, okay, so TensorFlow is just a clunkier version of NumPy that can run on a GPU. And that would be a perfectly reasonable assumption, but it's completely wrong.
And boom, here it is. This is the moment where everything clicks. When we print our NumPy array, we get what we expect, a grid of zeros. The math happened instantly. But when we print the TensorFlow tensor, we get, what is that? We don't get numbers, we get this weird object, this kind of symbolic IOU note that basically says, hey, I am a promise to create a grid of zeros later. Nothing has actually been calculated yet.
This right here reveals the absolute soul of TensorFlow. You are not doing math commands one by one. You are building a plan for all the math you want to do later. Like the official documentation says, you're defining a computation graph that has no numerical value until evaluated. It's a blueprint just sitting there on paper, waiting for someone to give the order to start building.
Okay, so if it's all just a plan, a blueprint, how do we ever get a real answer? Well, this brings us to TensorFlow's fundamental two-phase process. It's all about the blueprint and the engine that runs it.
Phase 1 is all about building that computation graph. This is the blueprint. You're like an architect. You sit down, you define all your inputs, all your variables, all the crazy math that connects them together. You drop this incredibly detailed plan for a skyscraper, but not a single shovel has hit the dirt yet.
Then comes phase 2, the session. This session is the engine. It's the general contractor and the construction crew. You hand it your finished blueprint, the graph, and you say, okay, build it. The session is what takes that abstract plan, grabs the resources like CPUs or GPUs, and actually performs the calculations to give you back concrete numbers.
So that's the whole workflow right there. It's really a simple two-step dance. First, you assemble the graph. You design the blueprint. Second, you fire up a session to bring that blueprint to life and actually get your results. Define, then execute. All right, so now that we get the process, what are the actual Lego bricks we use to build our blueprint? It really boils down to three main types of tensors you need to know.
First, you have constants. Just like they sound, they're fixed values. They're never going to change. Then you have variables. Now these are super important. They hold the state of your model. These are the knobs and dials, the weights and biases that the machine learning model is going to tune and adjust as it learns. And finally, you have placeholders. Think of these as empty pipes or entry points into your graph that you promise you'll pump data into later on.
And these placeholders are exactly how we get our real-world training data into the system. So in the blueprint phase, we define a placeholder for, let's say, our input images. Then, when it's time to execute, we use this little thing called a feed-dict, a feeding dictionary, to just pour our actual image data into that empty slot so the session can use it to do the math.
Okay, so let's put it all together. Let's imagine just conceptually how we build a simple machine learning model. We're not going to write lines of code that run one after another. Instead, we're going to design the blueprint for the machine itself.
See, this is the TensorFlow way of thinking. You just declare all the parts of your learning machine. Step 1, define placeholders for your data and the correct answers to flow into. Step 2, define variables for the weights and biases that the model is going to learn. Step 3, define the actual math that makes a prediction, and then calculates how wrong that prediction is. And finally, step 4, you define an optimizer, which is the part of the machine that will automatically tune the variables to make the predictions better and better.
And that optimizer, that's where so much of the heavy lifting happens. Because of that auto-differentiation thing we talked about, the optimizer can look at your entire blueprint, understand exactly how every single variable affects the final error, and then automatically calculate how to tweak them to improve the model. It automates the hardest, most error-prone part of machine learning. It's incredible.
So, after all of that, you gotta be asking, why? Why go through all this trouble of building a blueprint first? Why not just do the math right away like NumPy does? What's the big payoff here? What's the one thing you should walk away with?
The power, the absolute genius of this whole system is in separating the plan from the execution. Because TensorFlow gets to see the entire computation blueprint up front. Before a single calculation is run, it can do some amazing things. It can analyze the whole plan, find shortcuts, and optimize it. And most importantly, it can figure out how to chop up the work and run it in parallel across all your CPUs, or better yet, across hundreds or thousands of cores on a powerful GPU, giving you these massive, massive speedups.
And you know, this whole blueprint and engine idea is so much bigger than just machine learning. It's a whole paradigm for thinking about complex computation. It's a shift from just writing a list of instructions to actually designing a complete computational system. And that leaves us with a really exciting final question. If any computation can be thought of as a graph, what incredible blueprints are we going to design next?